Okay, so I've given you an overview of the research we did with whole numbers, and now we're going to talk about our extension of the work to rational numbers, and in particular fractions, though we've also done work with decimals and percentages, and occasionally I'm going to allude to that work, but mainly about fractions. So fractions provide children the opportunity to learn that features of whole numbers do not necessarily characterize all numbers. So children make a natural assumption that the way that whole number work will be the way that all numbers work, but that turns out not to be true. And when they run into fractions, one of the most difficult and important things that children need to learn is that many properties of whole numbers do not apply to other numbers. And fractions are very difficult for children around the world. There are surveys of algebra teachers, and there are surveys looking at various standardized tests, such as the TIMSS and the PISA, and in the US, the National Assessment of Educational Progress, all of which show that while countries differ in how well children score on these comparative assessments, the children all over the world have trouble with fractions. And math educators all over the world have commented that even though our children, for example, in Japan or China or Korea, they might say, well, compared to children in other countries, our children do relatively well. But in terms of what we want them to understand, they really are not all that good. And so this raises the question, well, why is it that fractions are so difficult? So in response to this challenge, Michael Schneider and Clarissa Thompson and I developed the integrated theory of numerical development. And this is intended to generalize and also to go beyond what we had learned with whole numbers to extend it to all kinds of numbers. So one assumption of this theory is that numerical development is in large part the generating increasingly precise knowledge of the magnitudes of an increasingly broad range of numbers. So you start out learning about the magnitudes of whole numbers and you extend it to increasing range of numbers, but you also have to learn about different types of numbers. And so we identified four main trends across the development from infancy to adulthood. One is from non-symbolic to symbolic numbers. So infants understand some things about non-symbolic numbers, like which dot display is more, but they don't know anything. If you show them the numbers 21 and 15, they have no idea how to deal with those numerals. Later, there's a progression from small to large whole numbers. There's also a progression, and it's the one I'm going to be emphasizing now, from whole numbers to rational numbers. Rational here meaning in terms of ratios, so numbers like fractions, percentages, decimals, and also from positive numbers to positive and also negative numbers. So that's one dimension, that's a basic assumption of this integrated theory. Another is that numerical development also is a process of learning that many properties of whole numbers do not apply to other types of numbers. So here's some examples. Every whole number is expressed by a unique symbol, but no fraction or decimal is. So when you look at 6, that's for a whole number, there's the Arabic numeral 6, and that's the only way in the number system to apply it. I mean, you can have other kinds of translations, like you can write out SIX, and I'm sure there's a character in Japanese that has 6, but it's only one symbol. Whereas when you start thinking about the same thing in terms of fractions, you can have 6 be 6 over 1, 12 over 2, 18 over 3, 600 over 100, and so on. And there are an infinite number of fractional and also decimal expressions of it, because you can keep on adding zeros. So you can have 6.0, you can have 6.00, you can have 6.000, and so forth. So that's one difference. Another difference is that every whole number has a unique predecessor and a unique successor, but no fraction or decimal does. So before 6, you have 5, after 6, you have 7, but after say 2/3, it's not a meaningful question to say what number comes before 2/3. Yeah, it doesn't make any sense to ask that, because there's no unique predecessor and no unique successor. Another difference, multiplying whole numbers never yields a product less than either multiplicand, but multiplying fractions or decimals that are between 0 and 1 always does. So if you are multiplying n times m, and you know they're both whole numbers bigger than 1, well, even if the whole number is equal to 1, it's not going to be less than the original numbers. Whereas with fractions, if it's between 0 and 1, and you multiply them, you'll always get a number that's less than either number being multiplied. And similarly, adding whole numbers never yields an answer smaller than either addend, but adding negative numbers always does. So that you add minus n and minus m, the number is going to be smaller than either minus n or minus m. So lots of unique characteristics of different types of numbers, and a general lesson that children need to learn is that the properties of whole numbers apply to whole numbers. Some of them apply to other types of numbers too. So as long as you're dealing with positive numbers, when you add whole numbers, the answer is always bigger than either addend. And when you subtract whole numbers, the answer is smaller than the original number. And that's true for fractions and decimals as well as for whole numbers. But you have to learn the particular properties and how they act with different types of numbers once you progress beyond whole numbers. So here's some example of children, the difficulty that children in the US encounter, and adults for that matter too, encounter with fractions. And to lesser degrees, children in East Asia also encounter these difficulties. It's not as big a problem, but it's still a problem from everything I've read. So when you give a task like about how much is 12/13 plus 7/8, and you ask as a multiple choice, is this going to be closest to 1, 2, 19, or 21? The most common answer among 8th graders, so these are not babies, these are 13 and 14-year-olds. The most common answer in the US is 19. And that was done about 40 years ago originally. Hugo Lortie-Forget and I did the same task because we were curious of whether we had made progress since 1981. And the answer was, oh yes, we have made progress. We progressed from 24% correct to 27% correct. So progress, but truly minimal. You know, basically the same problem as it was 40 years ago. A more recent national assessment of educational progress, again with 8th graders, only 50% of US 8th graders correctly ordered the 3 fractions that you see. Another one, this is with 11th graders. So these are almost done with the required schooling. Fewer than 30% of 11th graders correctly translated 0.029 into the fraction 29/1000th when they were asked which of several fractions was the right one to be equivalent to 0.029. Now, this is especially unfortunate because fractions are the most advanced math that most adults need to know in their occupational life. So a labor economist named Handel did a very interesting study. He looked at more than 2,000 people in the US labor force from all kinds of different levels of jobs. High level white collar, high level blue collar, low level white collar, low level blue collar, and service. And he asked them, do you have to do addition and subtraction of whole numbers as part of your job? And there about 85% said yes. Multiplication and division of whole numbers, almost as much. Fractions, decimals, or percentages, not quite as many, but still large majority. And then it really goes down. So when you get into algebra, geometry, statistics, very few people actually use those in their daily job life. So that fractions are the most advanced, along with decimals and percentages, kind of number that most people in the workforce use in their work life. So makes it particularly unfortunate that understanding of fractions is not very good. So in our first study of fraction knowledge, fraction magnitude knowledge, Clarissa Thompson and Michael Schneider and I looked at the fraction knowledge of middle income 6th and 8th graders. We gave them 0 to 1 and 0 to 5 fraction number line estimations. So we would present a fraction like 2/7 or 15/7 and ask them where on the 0 to 1 number line, or in the case of bigger fractions bigger than 1, where on the 0 to 5 number line these fractions should go. We also asked the children about to compare fraction magnitudes between 0 and 1, to do all 4 arithmetic operations with equal and unequal denominators for fraction arithmetic, and we obtained the children's math achievement test scores. So the fraction number line task looked like this. So on a 0 to 1 number line, you would ask, where does 3/5 go? On a 0 to 5 number line, you might ask, where does 17/5 go? The integrated theory made 2 main predictions: that if magnitude knowledge plays the same crucial role with fractions as with whole number, you would expect that knowledge of fraction magnitude should correlate reasonably highly with fraction arithmetic, because if you understand the magnitude, you can avoid mistakes like saying that 12/13 plus 7/8 equals about 1, which many children said, because you would say, well, 12/13 is about 1, 7/8 is about 1, 1 plus 1 is about 2. So, and they're both a little less than 1. So 12/13 plus 7/8, you would know that it's going to be a little less than 2. And so you're not going to say 19/21, you're not going to say 19, you're not going to say 21. You're going to know that it's going to be about 2. And similarly, the theory predicted that knowledge of fraction magnitudes should correlate highly with math achievement more generally. So if we think about algebra, you would know, if you understood magnitudes, that if 3/4 of x equals 6, that x is going to be a little bit bigger than 6, because 1x is going to be bigger than 3/4 of x. So the x has to be somewhat bigger than 6 in order for that equation to work. So here are the results that we got with 6th graders between the correlations between arithmetic accuracy and math achievement. And you might wonder, well, why are the top 2 rows negative correlations? Well, we're looking at percent absolute error here. And with number line estimation, the lower the percent absolute error, the more accurate you are. so that if you're perfectly accurate, your percent absolute error would be 0. So if you put 3/5 exactly at 0.6, that would be a percent absolute error of 0. And the bigger the number, the error is, the worse the estimate. And so that's why those correlations are negative. But as you can see, all the correlations with magnitude 0 to 1 number lines, 0 to 5 number lines, and magnitude comparison correlate pretty substantially with both arithmetic accuracy, and this is fraction arithmetic, and math achievement overall on the tests. And it turns out that this is at least as true with the 8th graders as with the 6th graders, maybe even a little more true. So here are the data with the 8th graders, same data, just different participants. And you can see that, again, really quite strong relations between knowledge of fraction magnitudes and both fraction arithmetic performance and overall fraction math achievement. So this was consistent with the integrated theory's prediction that the magnitude understanding ought to correlate with arithmetic and overall math knowledge. Now, along with a group of others, Greg Duncan and Pam Davis-Keene, important among them, we looked at whether early fraction knowledge, that is knowledge in 5th grade, so when the kids are about 10, is uniquely predictive of later math achievement. And later math achievement here was looking at 10th graders who are about 15. And we looked at whether, we reasoned that fractions, including ratios and proportions, are heavily emphasized in high school math. Algebra, geometry, trigonometry all use fractions a real lot. And we asked whether individual differences in elementary school students' fraction knowledge uniquely predicted high school students' algebra and overall math achievement, because if fractions indeed do play a central role in subsequent math learning, that how good you are in fractions early on will contribute to how good you are in more advanced math later on. So to find out, we examined the unique contribution of 5th graders, whole number arithmetic, fractions, socioeconomic status, IQ, and working memory to math achievement and algebra knowledge in both the US and the United Kingdom, Britain, in 10th graders. Here's what we found. So these are standardized beta coefficients. And as you can see in red, fraction knowledge in 5th grade made unique contributions to, this is the British data, to both algebra and total math knowledge, above and beyond whole number arithmetic and socioeconomic status and IQ and working memory. And division also did. And this really surprised us because to us, fractions and division are kind of the same thing, right? I mean, what 12/13 means is 12 divided by 13. But obviously, the fact that division made an independent contribution from fractions and fractions made an independent contribution from division meant that to children, they're not. Now, we have some speculations about why this is true. We can talk about those later if you like. And then these other contributions were not significant. Now let's look at the US data. Here, the only significant predictors were fractions and division, and both of them were contributed both to algebra and to total math knowledge independently. So we started wondering, going beyond procedures, do children understand fraction arithmetic? So it's possible you can do well on a standardized test if you just memorize the algorithm or procedure. And many children do this. So, but we were interested in whether they really understand what they're doing as opposed to just memorizing. And so we used a task that is called the direction of effects task. And the idea is, if you understand arithmetic procedures, at minimum, you should understand their direction of effects on magnitudes. So for example, if you understand fraction multiplication and you're asked true or false, is 13/15 times 11/17 greater than 13/15, you ought to be able to say no, because multiplying two fractions less than one will produce an answer less than either of the fractions. And the 13/15, we always used the bigger of the two fractions as the comparison point. So if the number had been 7/8 rather than 13/15, we would have said is 7/8 times 11/17 greater than 7/8. And so we presented problems with fractions above 1 and fractions below 1. So when you multiply fractions above 1, the answer is always going to be greater than either fraction. But when you multiply fractions below 1, it's going to be smaller. So one experiment that we did was with pre-service teachers. These are teachers who are in their last year of education majors in college, and they'll soon be teaching children. And as you can see, the children, or rather the pre-service teachers, they're adults, did quite well for all the kinds of fractions above 1, and they did fine with addition and subtraction of fractions below 1 either. But they did very poorly, actually less than chance, when multiplying and dividing fractions below 1. Now, why would you get this pattern? Well, if you would ask yourself, how would it work with whole numbers? The whole numbers conform exactly to the pattern of fractions above 1. And people did fine on those. And addition and subtraction also conform to the pattern with whole numbers, but multiplication and division of fractions go in the opposite direction when the fractions are below 1. And that's where you had below chance performance. So what the teachers were doing was generalizing their knowledge of whole numbers inappropriately to knowledge of fractions. We also gave the same task to 6th and 8th graders and found very similar results. The 6th and 8th graders, somewhat to our surprise, actually did a little better than the pre-service teachers. But like them, they did very well on the kinds of problems that followed the whole number pattern and did below chance on the problems that did not follow that pattern, namely multiplication and division of fractions below 1. Now, we wondered, is there something wrong with this task? So when I ran this study, I was at Carnegie Mellon University. Students are very good at math at that university. And so we took a group of students and gave them the problems. And as you can see, they did just fine on all the kinds of problems. They had no difficulty at all. So there was nothing wrong with the task. It's that the people's knowledge, both the children's knowledge and the pre-service teachers' knowledge, was lacking for multiplication and division of fractions below 1. Here you can see that the same pattern that we found with fractions also holds true on decimals. So it's not that something about fraction notation causes this problem. It's more a fundamental failure to understand rational numbers and how they work in the context of arithmetic, multiplication, and division. So these results were not due to ignorance of rational number arithmetic procedures. The preschool service teachers, when we gave them rational number arithmetic. And when we say, so what is 4/5 times 13/15, they were almost perfect on it. It wasn't due to ignorance of the magnitudes of individual rational numbers. So when we asked teachers, where is 13/15 on the number line, the teachers again were almost perfect, just as good as with whole numbers. And it wasn't confusion about fraction notation, because their decimal arithmetic knowledge was just as bad as their whole number, as their fraction knowledge. So that none of those counter explanations really fit the data. So thinking about these results made us think more deeply about rational number arithmetic and why it's so hard for children and indeed for adults to understand. And the magnitude and arithmetic knowledge are correlated, but knowledge of individual fractions and decimals seems insufficient to estimate arithmetic answers accurately. And the fact that you get these classic errors like 12/13 plus 7/8 equals about 1 or 19 raises the question of whether children use the magnitude knowledge they have when they do rational number arithmetic. So even if the children understand the individual fractions, even if the pre-service teachers understand the individual fractions, do they really apply that knowledge when they're doing arithmetic? So along with this, we were asking, why is fraction arithmetic so hard to understand? And we divided the reasons into two types: inherent reasons that fraction knowledge would be hard to obtain no matter what the society was, and culturally contingent reasons that would be, whether it's going to contribute difficulty depends on the particular society in which the children are learning about fractions. So no matter what society you live in, it's somewhat difficult to extract the magnitude of fractions. So if you say, how big is 37/83? That's kind of hard. You know, even if you understand what fractions mean, the notation is kind of difficult. And so you can simplify it, as was suggested earlier, and you could say, well, 37/81, that's about 40%. And so you could say it's about that, but I'm not at all sure that that's right. I just made up 37/81 out of my head. I know it's going to be less than, it's going to be less than half, and it's going to be greater than a third. And that's the only thing I'm really sure about. There's also a complex relation between whole number and fraction arithmetic operations, so that in some ways they're the same, but in other ways they're different. So you can multiply the numerators and the denominators within fractions just as you would multiply the whole numbers, but you can't do that when you add and subtract fractions. You can't add the numerators and add the denominators. And so those relations are kind of tricky. And there are complex relations among fraction arithmetic operations. They differ in how they work in kind of complex ways. So when you add and subtract fractions, you maintain the denominator if you have equal denominators to start with, and you translate the fractions so that they have an equal denominator if you don't start with an equal denominator. But with multiplication and division of fractions, there's no reason to do that. You could do it, it wouldn't do any harm, but it would be a waste of time and effort. And then there are culturally contingent reasons that'll vary from society to society. So in some societies, teachers have better understanding than others. So Li Ping Ma did studies of Chinese and US teachers and found that Chinese teachers knew a real lot more about fraction arithmetic and fractions than the US teachers did. There are differences in textbooks in different countries. Some explain concepts better than others. So for example, Singapore math has particularly clear explanations of how fraction arithmetic and other subjects for that matter works much better than US textbooks, which are really quite confusing. And student prior knowledge differs. So even before children get to fractions, children in some societies like Japan have better whole number knowledge than children in some other societies like the US. So in order to study the effects of textbooks, we identified 3 popular textbooks, widely used textbook series in the US. And we looked at their frequency of equal denominator and unequal denominator fraction arithmetic problems with each of the 4 arithmetic operations: addition, subtraction, multiplication, and division. And we looked at how frequent problems of each of these 8 types were. What we found was that in all 3 of the textbook series, the multiplication and division of equal denominator fraction problems was very uncommon. There were hardly any problems like this in one of the textbook series. There were literally no fraction multiplication problems like 3/5 times 4/5. So we were interested, and there were other biases in the textbooks too, and we can talk about this at the end if you'd like. But this is one example of the kind of biases that I don't think anyone tries to do this. I think this is totally unconscious and unintentional, but nonetheless, the children can only learn the problems that they're given. And if you're a good math student, maybe you generalize appropriately beyond the problems you're given. But if you're not such a good math student, you won't learn types of problems that you're not presented. And so we were interested, David Braithwaite and I, in the disconnect between magnitude knowledge for individual fractions and fraction arithmetic, because we had noticed that the children and teachers were better at individual fractions than at fraction arithmetic, but we didn't have a good comparison. So this is what we did. We looked at number line estimation of individual fractions and whole numbers, and also of sums of fractions and sums of whole numbers. So we had 18 fractions between 0 and 1. We had 18 whole numbers, which were the fractions times 1,000. So if the fraction was 5/8, for example, we would multiply it times 1,000, and the whole number equivalent would be 625 on a 0 to 1,000 number line. And so the sums were 16 unequal denominator fraction arithmetic problems with the same fractions, and 16 whole number fractions sums. And the whole number sums were the fraction sum times 1,000, again, with the same whole numbers. And the children were 11 to 13-year-olds. So they were, again, 6th, 7th graders. And this is what we found, that if you look at the whole number percent absolute error first, the children were pretty good on both the individual numbers on the number line, saying where 5/8 would be, for example, and I'm sorry, where 625 would be, and in the addition problems, like what would 625 plus 275, where would that go? But when you did the fraction equivalence, you see that, first of all, they were worse with both the individual numbers and the sums of numbers, but they were much worse with the sums of fractions. That's where they really had problems. And in fact, when you, to give you a feel for just how bad their estimates of the sums of fractions were, if on the number line task, you would say every sum will be at the midpoint of the number line. So every sum would be at 1/2. Your mean percent absolute error would be 25%. The children actually did slightly worse than that, because there was some random element. Rather than putting everything in the middle, they would put things all over the number line in ways that were really uncorrelated with the actual magnitudes when they were asked to estimate the sums of the fractions. Another index of the same problem, 52% of trials, children estimated that one or both fraction addend was larger than the corresponding sums. So we gave children the equivalent numbers as addends and as sums. So we, for example, gave children 2/9 as a fraction, and they estimated that. And we gave them 3/7, and they estimated that. And then we gave them where would 2/9 plus 3/7 go. And then in these triplets of problems, 52% of the triplets, the children estimated that one or both individual fraction was larger than the sum of the fractions. So they would estimate that either 2/9 or 3/7 or both were bigger than 2/9 plus 3/7. So they really, when it comes to estimating the sums of fractions, they have no idea. They're really about at chance. So what can we do about this? So David Braithwaite and I recently did a study applying the game Catch the Monster with fractions. And what we did in this game, it was a follow-up of an earlier game that we had done, Lisa Fazio and I had done. This version was better. And what we would do, we first used the strips of paper of different color that you see on the left top. So 1/2 had the longest strip, and 1/3 had somewhat shorter, and 1/4 somewhat shorter. And all of these were associated, all the fractions were associated with different color strips. And then we taught the children how to create bigger fractions with bigger components out of the smaller component fractions. So 3/10 could be created, as you can see in the middle here, of 3 1/10 strips. So that's what 3/10 means. Even though people very rarely, in the US at least, think about what 3/10 means is 3 of the 1/10 units. And what 2/4 means is 2 of the 1/4 units. But that is what it means. I don't know why we don't teach children this, but at least in the US, we don't. And so we thought that teaching them that fractions could always be the combination of components of unit fractions of 1/n, that we thought that this would help them estimate both the individual fractions and the sums of fractions better. And so we played a game where there was a number line, and we would ask them questions like, where would 3/10 plus 2/4 go on this number line? And if the child was right, the monster shown at the bottom here would be caught in the cage. But if they were wrong, the monster would make fun of the child and tell them how dumb they were. God, you didn't get me. You're not good enough to get me. And that's the way the game worked. And the kids really liked the game. They played it as long as we would allow them to. So we presented 104 fifth and sixth graders to either fraction sum games or whole number sum games. And the fraction games, they were given problems like estimate 1/3 plus 2/9. And in the magnitude comparison, they were asked is 1/3 plus 2/9 greater than 1. And these are the results. So on the number line estimation, the children got a real lot better on the fraction sums, as you can see on the left side here. They went from results that are almost identical to that earlier study that I mentioned, where they were at chance or maybe even a little worse, to very respectable performance on the post-test. Now, and I should add, on the post-test and the pre-test, they didn't have these strips available, but they had been taught to use them, and so they could imagine them, and that's what they were doing here to generate the better performance. On the whole number sums, as you would expect, given that their knowledge was pretty good to start with, they didn't improve much. In the fraction sum magnitude comparison, where we asked them if one fraction plus another fraction was greater than or less than another fraction, they improved a real lot on the fraction sums again, from about 65% right to a little over 80% right. Whole numbers they were good at from the beginning. So we found that we were able, in relatively short time, I mean, this was only one session of about a half hour, they were able to really improve their performance quite a bit. So 4 conclusions to end the talk. First of all, magnitude knowledge plays a large role in understanding rational numbers, as it does with whole numbers. Thus, it's a useful theme for a unified theory of numerical development. Second, rational number magnitude knowledge and arithmetic are strongly correlated, but most children do not use their magnitude knowledge when given rational number arithmetic, because otherwise their estimates would be much better of rational number sums than they are. Third, textbooks with biased distribution of problems contribute to poor fraction arithmetic learning. We've seen this not only with the 3/5 times 4/5 problems, where the children are worse on doing problems where the fractions have equal denominators by quite a bit than they are at fractions that have unequal denominators, even though the procedure is identical for the equal and unequal denominators, but the children do worse. And this is true in a lot of different problems where we've identified textbook biases, where certain kinds of problems aren't presented much. The children do poorly on those kind of problems, even if the procedure is identical, regardless of the type of problem. And finally, more generally, insights from cognitive science have already led to successful intervention for improving understanding of both whole numbers and fractions, and further insights from cognitive science can do so in other mathematical areas as well. Thank you.